Hello everyone, welcome back to the channel. So today we will be taking a look at this question called the checkposts, which is uh, present in the this A2OJ ladders list. Okay, so let us take a look at the problem statement. I definitely recommend you to try this problem on your own, and if you are not able to solve, here's the solution. Okay, so if you have understood the problem statement, you can directly skip to the solution part. Okay, there are timestamps below the video. Okay, so your city has n junctions. So problem states that your city has n junctions. There are n one-way roads. So one-way roads, not two-way roads. So between the junctions, as a mayor of the city, you have to ensure the security of all the junctions. To ensure the security, you have to build some police checkposts. So checkposts can only be built in a junction. A checkpost at junction I can protect junction J if either I is equal to J or the police patrol car can go to J from I and then come back to I. Okay, so there must exist a loop kind of a thing. So building checkposts costs some money. As some areas of the city are more expensive than others, building checkpoints at some junction might cost more money than the other junction. So we have to determine the minimum possible money needed to ensure the security of all the junctions. Also, we have to find the number of ways to ensure security in minimum price and in addition in the minimum number of checkposts as well. So two ways are different if any of the junctions contains checkpost in one of them and do not contain in the other. Okay, so in the output we will be given n and the vector or the array which contains the value of the station to if it is built in the ith city. Then we will be given m, which is the number of edges or one-way roads you can say, and then the description of the edges. So u comma v means there is a directed edge going out of u and landing at w. Okay, v. Okay, going from u to v. Okay, so let us take a look at this sample test case. So today I will be using this tool called the what you can say graph editor, online graph editor. So okay, so here's the website. Let's take a look at this sample test case. Okay, right, and the graph is directed. So let us try to unwind this graph. Okay, okay, looks fine, I think. Yes. Okay, so by seeing at this graph, what we can notice is that uh, so here we can see that we must make or we must establish a station here, or what was it? So checkpost. Okay, we must ensure that there is one checkpost here. So this dark circle is denoting the checkpost, because there is no way that you are going to 2 from any of the nodes 1, 3, 4 or 5. So there must exist an independent checkpost at the 2, right? So that's the thing. And so this thing 1 3 4 5, this thing is strongly connected components. Do you agree? These 1 3 4 and 5, these four nodes are basically the strongly connected components. So basically if you try to establish a checkpost at the 1, it can visit or it can secure all the junctions 3 4 5. If you try to establish a post on check 4, it will secure all the junctions 5 1 3. So basically what I can notice is that when I have an connected component, then I can just build one checkpost in that whole connected component. Make sense? Yes, absolutely does. And where should I establish that checkpost? So the node or the junction which has the minimum value of all 1 3 4 and 5. So for 1 3 4 and 5, so minimum is 0, right? So basically we will establish a checkpoint at 3 and 2. So to establish a checkpoint at 2, we need 8 units of cost, and to establish a checkpoint at 3 or 5, we need 0 units of cost, right? And that is why our cost is 8 plus 0 8. And what are the number of ways to achieve this cost and the minimum cost and the minimum number of checkposts? So instead of 3, I could have also established a checkpost at the 5, right? Why? Because the cost to establish a checkpoint at 3 or 5 is same, right? Because it is basically 0 or 0. But if it was 1 for the 5, then our this answer 2 won't be 2, right? It would be 1, because there will be only one way in this strongly connected component uh, to have a checkpost, right? So it will be at 3. So if in the case the fifth value in this array was 1, but it is not, so that's why 2 here. So I think the intuition behind the solution is clear, right? So you will find all the connected components, strongly connected components rather, I would say. You will find all the strongly connected components in this graph. There are two strongly connected components, which are 1 3 4 5 and the 2 itself, and from the every strongly connected component you will take the minimum cost to establish a checkpost anywhere in that strongly connected component, right? And also it would contribute towards the first argument of your answer, right? And for the second argument of your answer, you will count how many nodes are there with the minimum value in the strongly connected components. So here it were 2, right? So this 3 and 5 were of the same weight, which was minimum. So that's why in our case answer was 2. I think it makes the solution pretty clear. So we can directly head towards the code to understand what's really happening. So for those of you who you don't know how to calculate the strongly connected components, I would definitely recommend you to watch some tutorial based on the strongly connected components. It is basically called the Kosaraju's algorithm. Okay, and if you don't know really how that works, let me give you a brief idea. Okay, so suppose there are strongly connected components in the graph. So strongly connected component 1, strongly connected component 2, strongly connected component 3. Okay, so suppose here it is node 1, here it is 2, here it is 3, here it is 2, like this. Okay, and suppose here it was 4, here it was 5, and there was another triangle here. So suppose like this. Okay, makes sense. So okay, let it be this way. Okay, so in this graph there are how many connected components? This one, this one, and this one, right? So there are three connected components, right? So connect number of connected components, or strongly connected components, I would say, is 3. Okay, so how do we find that? So we perform the DFS on 1. So what I can notice is that when I start to perform the DFS on 1, so when I start to perform DFS on 1, so suppose I go to, what you can say, I go to 3, I go to 2, I go to 4, I go to 5, I go to 6, I go to 7. Okay, so basically I am visiting all the nodes 1 comma 2 comma 3 comma 4 comma 5 comma 6 comma 7, right? So basically when I am trying to perform DFS from 1, I am visiting all the nodes. Okay, but when I try to perform the DFS on 7, when I try to perform the DFS on 7, it is not visiting all the nodes, right? So it will visit 5, it will visit 6, and it will stop the DFS which started at the 7. So this will give you the strongly connected component 5 comma 6 comma 7. Okay, so how do I know that from what node I have to start the DFS to get these strongly connected components? So for that we need to store the stack of long, you can say, stack of the nodes. So suppose you start the DFS at 1. So you go to 3. Okay, so you go to, first of all you go to 1, then you go to 3, then you go to 2, I would say, then 4, then 5, then 6, and then 7. And by performing the DFS, you will calculate this order, and you will calculate this order and start from the behind. Start applying DFS from the behind, and so you will apply DFS on 7. So these nodes will get visited 7, 5, 6. Then you won't perform DFS on 6 and 5. 7 is already gone. Then you will perform DFS on 4. So it will be another strongly connected component, and then you will perform DFS on 2. So it will visit 2, 1, and 3. So that is basically another connected component, and you'll strike 3 and 1 because they all are visited and your stack is over. So you will stop performing the DFS operations. Make sense? So that is basically the whole idea of the Kosaraju's algorithm, I would say. This is the whole idea behind Kosaraju's algorithm. Okay, And okay, so I think that's enough of the explanation on the strongly connected components. So while performing this, what you can say, uh, DFS, while performing the DFS on the stack, okay, so you need to reverse the edges. Okay, so basically what I am trying to say is that, so there is this strongly connected component. So if this is the strongly connected component 2 and this is the strongly connected component 3, okay, suppose these are the edges that exist between these strongly connected components. Okay, so wait, so I have done a mistake here. So you won't be having stack in this direction. Okay, so you won't be having stack like this. Okay, so you will have stack like this and you will start from here. Okay, so sorry for that. Okay, so you will start again from the 1, so you will start applying DFS again from the 1. So basic idea is that, so here are your strongly connected components, and when you try to apply DFS on the node which is in the strongly connected component 1, it will traverse all the edges, but when you'll reverse the edges, it won't be anymore traveling to the other strongly connected components. Are you getting my point? Okay, so when this strongly connected component is reported, we will start DFS here in the SCC2. It won't go to SCC1 because visited array is already marked as true for all the elements here, and it won't go into this strongly connected component. Okay, it won't go into this strongly connected component because there is no such edge, right? No such this edge. So that's how you try to, what you can say, calculate the strongly connected components. Okay, so mod is for this thing. We have to do the modulus operation for the second argument of our answer. Okay, n is basically the maximum n that we will have, and this is the graph, the straight graph. Straight, what do I mean by straight is that without reversed edges. This is the graph without the reversed edges, and this is the graph with the reverse edges. So while taking the input, I am not reversing the edge in the first graph, but I am reversing the edge in the second graph. As you can see, I am changing the order of the arguments x comma y. So x is here, y is here, y is here, and x is here. So that is basically the thing. And visited array, firstly initializing it with false, and this is stack for our first kind of DFS, and this vector store will store the strongly connected components. Okay, so we'll see. And this DFS1 is for the second type of DFS, which will run on the inverted graph. Okay, makes sense? Okay, so yes, and while performing this second DFS, I am also calculating the nodes. So I am also collecting, I would say collecting the nodes present in that strongly connected component. Okay, and pushing it to the store. Okay, so that connected component will be pushed into the store, and I will clear that connected component for the further usage. So I am declaring it globally, and I am clearing it whenever it is used one time. Okay, so basically taking the input, if so performing the first type of the DFS operations, to fill up the stack. So we are filling the stack here. Okay, that is basically the Kosaraju's algorithm states to do so. And after filling the stack, we will again initialize visited array with the false, and while stack.size is greater than 0, we will collect the topmost element, and if that is not visited, simply run the second type of DFS on that node element and push the connected components and clear that connected component for the further usage. Okay, and here comes the most interesting part. Not most interesting, I would say somehow clever. So I am referencing the element from this store vector. So basically referencing every strongly connected component in the store vector, which stores all the strongly connected components. I am picking every entry from that strongly connected components by reference and assigning it to the v of entry. Okay, why am I doing that? So basically you'll get to know here. Okay, so I can directly add the mini. So I can directly add the mini here in this for loop. Why mini? So we want to add the minimum cost to establish a checkpost in that what you can say, in that strongly connected component, right? So that is why first uh, changing all the entry values to their costs and checking the costs and minimizing them whenever possible and adding it to the answer and checking how many minimum costs are possible, right? So how many minimum costs are possible in that strongly connected component, and we will try multiplying it with our answer, the second argument of our answer, and simultaneously taking mod as well. So this sentence or this statement basically follows the AND principle of the combinatorics. And yes, finally outputting A, which is the first argument of the answer, and the B, which is the second argument of the answer. And yes, it nicely passes in the time limits. And yes, I hope you enjoyed solving the problem on your own and listening to the solution as well. Thank you for watching. Thank you for watching again. And if you found this solution useful, you enjoyed watching the solution, consider liking the video and staying tuned, staying subscribed to the channel as well. Okay, see you again.